All right, we've got a few more things to put with our picture here, just to kind of cap it up with what we got. I want to show you the Lewis dot structures. So the Lewis dot structure of Na, this really brings it back in where we're going here. Here's Na and has one valence electron. As you remember, Lewis dot structures show you the number of valence electrons that they have. I could have put that dot on the side, on the top, the left, or the bottom. It really doesn't matter. I chose to put it on the side because it seemed like a good idea to me. Na as an ion would be Na 1+. It loses its outer electron, so we don't show it at all. Now we know it has a new kind of like valence electrons, but we don't really show that one. We always show its outermost energy level at any one point. So I've got Na as the ion, Na as the atom. Now if we think about chlorine, chlorine as the atom, chlorine actually has 7 valence electrons. 1, 2, 3, 4. I want to put 1 on each side and then start doubling up 5, 6, 7 until I've got them all on there. And that's to follow the Pauli exclusion principle. That was a rule that you have for electron configurations, that you don't want to double up electrons in an orbital unless you have to. They don't really like to have the electrons by each other. Electron repulsion isn't so great. Our chlorine ion over here, it's a chlorine 1-, it's an anion. So we got chlorine 1, 2, 3, 4, 5, 6, 7, and I gained 1 electron, so that makes 8. Now there's a lot of dots around here, so to show that all those electrons belong to chlorine, we put brackets around it and give it a 1-. Now if I wanted to show what NaCl looks like, NaCl would be the Na 1+, and the chlorine 1, 2, 3, 4, 5, 6, 7, 8 with a 1-. Things might get a little trickier if you want to do like MgCl2. We would use Mg, it would have a 2+ charge. Chlorine would still have your 8. And you'd want to put that 2 out in front to say you have 2 of these chlorine ions. Just trying to bring it back for you. So that would kind of finalize our picture a little bit there. But I also want to add things about Coulomb's law to it. Now there's 2 parts of Coulomb's law to this, to be honest. I want to bring myself just to NaCl. Coulomb's law applies in 2 spots. The first spot I want to talk about is what we've already covered. This outer electron here is attracted to the nucleus, and that attraction is according to Coulomb's law. So Coulomb's law, if we remember, is K, Q, Q over D. This K is a constant. The Q is the 1 charged particle, so I'm going to call that my electron here. It has a charge of a -1. This other Q is the other part that's attracted to. We know it's the nucleus. The nucleus is right here in the center and has 11 protons, so I'll call that 11+. Now we're not actually going to calculate this, but those are what those numbers are. And then the D is the distance between the nucleus and that outermost electron, because this is the one I'm looking at. So this attraction here between the electron and the nucleus is what holds the atom together. Coulomb's law holds the atom together, that attraction. There's another kind of Coulomb's law we got going on here, actually. We just drew the chlorine ion and the sodium ion. And these 2 ions right here, the electron was given up by the sodium to the chlorine, and now they have this attraction to it. So here I've got my Na ion and my Cl ion. There's an attraction between these 2 ions. It's a Coulombic attraction, actually. Let's bring it back to KQQ over D. K is again a constant. My Q now is going to be the ions. I'm kind of looking at it from a bigger perspective, kind of like taking a step out. Now my first Q is going to be my Na ion. It's a 1+. My second Q is going to be the Cl ion. It's a 1-. Okay, my K is my constant. Q is a 1+. This other Q is going to be my -1, cation, anion. And then my D is going to be the distance between this ion and this ion. We kind of have to think of it, Na, remember, is a smaller circle, chlorine is that bigger ion. So the distance between these 2 parts kind of here. That's how they kind of, I know that the 2 nuclei aren't attracted to each other, but they're looking at this distance. That's called the lattice energy. But this is going to be Coulomb's law, and this part here, that attraction that it feels, is what our ionic bond is. The ionic bond is the attraction it feels between the cation and the anion, according to Coulomb's law, that attraction. It can apply to 2 spots. You can look at it with just the atom, or you can look at it now that we have a bond. And this unit is all about bonds, so we're going to start thinking about it from this perspective. How is this ion and this ion, or this atom and this atom, when we get to molecular, how are they attracted to each other? Let's take it to lattice energy. You'll find this in your notes. but it's the energy required to completely separate a mole of a solid ionic compound, we're specifying ionic compound here, into its gaseous ions. So here you can see, here's my Na, here's my Cl. They're attracted to each other, and they're attracted by, of course, Coulomb's law. We're going to look at the two things that are affected. Well, the only things that are going to affect how the lattice energy is something that has to do with Coulomb's law. You're not going to change the K, that's a constant. So really we got to look at the Q, or we got to look at the D. Let's take a look at this one here and try to figure out what's changing as we go. Is the Q changing or is the D changing? The Q would be the charges of the ion. If I look at the charges of these ions, lithium's a +1, sodium's a +1, potassium's a +1, and cesium or cesium's a +1. On the other side, fluorine, chlorine, iodine, fluorine, chlorine, bromine, oh, they're all -1. All of these have a +1 and have a -1, which means my distance is the thing that's changing. If I'm thinking about distance, then I'm thinking about ion size. Remember, we're kind of looking at it from this perspective. See how this guy's really big and like fat and wide? That's a big distance for him to send out his like attractiveness, if you will. And this guy's got a short distance. So let's think about the size of these ones here. So I just kind of want to look at something that's similar, I guess. Let's just look at the lithium guys. So lithium is the same for all these, but fluorine, chlorine, and iodine are different. Fluorine on the periodic table is most towards this top, so he's the smallest. Iodine of these three is the largest. He's the most towards the bottom of the periodic table. So I can see that as I become larger, my lattice energy has decreased. There's a lower amount of attraction. That seems to make sense according to Coulomb's law. So Coulomb's law would support the idea that as you increase the size of the ion, that'll lead to a decrease in attraction. According to Coulomb's law, and that decrease in attraction, or just the idea of Coulomb's law, means we're going to have a decrease in lattice energy, because lattice energy is defined as the Coulombic attraction between those two ions. Okay, let's look at our second trend here. Again, it has to apply to KQQ over D because that's what lattice energy is kind of calculated as. If I look at these parts, I've got Mg. I've already covered D, so you know we're going for Q. Mg is a 2+, and chlorine's a 1-. Sr is a 2+, and Cl is a 1-. I've got MgO as a 2+, and now I've got a 2-. 2+, 2-. Towards the bottom here, I've got a 3+ and a 3-. So I could see that I've got higher charges at the bottom than I do at the top. This part here is a small number compared to this number way down here. This is huge. I have a large lattice energy. That means I have a large Coulombic attraction because my Q's are going from a +1, -1 to suddenly a +3. If my Q becomes a +3, that's like a 3 times larger magnet here. It would make sense that you'd have this big sort of jump. As we increase the charge of the ion, I can see that my Coulombic attraction is greater, which is why my lattice energy, that value, that number in this table, is also increased. That would be my summary part for this part. You have textbook questions that deal with this same topic, so hopefully this helped you out.